Alright, so in this video I'm going to show you how to derive the formula for finding the centre of mass of a one-dimensional body. So we're going to say that this one-dimensional body is a light rod with 4 point masses on it as shown. So that just means that at this specific point there is a mass of 5 kilograms that doesn't have any dimensions either way. Here there's a mass of 3 kilograms, here there's a mass of 2 kilograms, and here there's a mass of 10 kilograms. So if I want to find the centre of mass of this object, what I want to find is the point at which I could put a support and it wouldn't tip. It would be completely in equilibrium. So let's just imagine that I'm going to put the point, now probably it would be somewhere kind of over here, because that 10 kilogram mass is going to be quite heavy, so it's going to make it want to tip over there. So it's probably quite far to this side, but it doesn't matter if we perfectly predict where it's going to be. But let's say if we were going to put a support there, there would be a reaction force at that support, and there would be weight forces, or well, reaction forces acting downwards from each of the point masses, as I am labelling here. Okay, and those would be all of the forces on the system. Now I can very easily find the magnitude of this reaction force just by resolving vertically. Okay, so I'm going to know that that reaction force is going to be equal to 10g plus 2g plus 3g plus 5g. Just equal to the sum of all of the downwards forces there. So, which is equal to 20g. Okay. Now, it not only needs to be in equilibrium in terms of the forces balancing vertically, it also needs to have a total moment of 0, as we know. So it might be tempting to take moments about this pivot point, but since we don't know where it is, that's going to create a lot of messy algebra with lots of different unknown distances. So what is going to be easiest is actually to label an origin. So let's say there's an O there, and let's say we want to find out where the centre of mass is in relation to that. So we're going to actually call that distance x bar. That's often what we call the distance of the centre of mass from the origin, x bar. So we're going to label that on there. Now if we take moments about O, let's say the clockwise direction is positive for now. So that 5g is not going to have any effect because that's acting directly through O. But this 3, but let's write it on there just in case. So 5g times 0, then we've got plus 3g times, that's 2 meters away, so that's times 2. Then we've got this 2g times 4, because that's 4 meters away. And then we've got the 10g times that total of 7 meters away. And that's going to be equal to, because the r is going to go in the other direction anti-clockwise, that's going to be equal to r times that distance which we have called x bar. Now we already worked out the size of the reaction force, that's 20, so that's going to be equal to 20g x bar. And adding up all of these, we will have 5g plus 6g plus 8g plus 70g. Now we might already notice that g in fact cancels from everything, so that makes things a bit easier. So our total here is 5 plus 6 plus 8 plus 70. 8. Oh, that was times 0, so that should be gone. So that's 84 equals 20x bar, which means that dividing 84 by 20 gives us 4.2 meters. So that means that the support would have to be placed about 4.2 meters away from the origin, which means that the centre of mass is 4.2 meters to the right of the origin. Okay, so centre of mass which means that I did draw it in roughly the right place. But it wouldn't matter if you'd drawn it over here, you would still end up with the answer of 4.2. You would just, it wouldn't matter at all. Now, what I want to do, this was just an example of how to use moments to find the centre of mass, but we can actually generalise this a bit more. So let's, what do? We found, we were trying to find here, so this, on this side, this was the moment of R at the centre of mass, because that was the point we had to put it at, and that was equal to the total moment of individual masses. Okay, or the sum of the individual masses. So the moment of R was R times x bar. And now what was R but actually just the sum of all the weight forces? So if we, instead of having specific amounts, if we said we had, if we were adding up M1 plus M2 plus M3, however many we had, we multiplied that by G, and then we multiplied that by x bar, the distance from the origin of the centre of mass. That was equal to the total moment, which was M1, so each mass times by its distance from the origin, and however many of those we might have, times by G. Now G cancelled, so we're left with what we can write here as the sum of the masses. So it's often written like this, sum of mi, and now that's starting from I equals 1 to n, however many point masses you might have, times x bar equals the sum of mi xi, so that's each mass times its distance, and again that's from I equals 1 to n, however many point masses you have. So we can then write that even more simply as just the distance of the centre of mass from the origin is equal to the sum of the point masses times their distances from the origin divided by the total mass. Okay, and in practice, this is the formula that you will want to use. Generally, you wouldn't necessarily want to go through all of this, because doing all this, G will always cancel if you're just talking about masses. And this is a lot longer. What you will often do is actually just substitute straight into here. So we can do that actually for this example as well, just to see what that would look like. So the centre of mass is equal to the masses times their distances, so that's 5 times 0 plus 3 times 2 plus 2, so 2 meters away, and 2 is 4 meters away, plus 10 times 7, divided by the total mass, 5 plus 3 plus 2 plus 10, and then straight away that will give us, obviously it's the same calculation, it'll give us exactly the same answer, but it will give us 4.2 meters. Okay, and that's much shorter, but I wanted to show you where it came from by doing those moments before. But this is the formula for the centre of mass. So it's the distance of the centre of mass from the origin is equal to the sum of the individual point masses times by their distance from the origin divided by the sum of the masses.